Now I would like to demonstrate the solution to exercise 3. You are asked to perform k-means clustering to segment the T2 weighted image of the brain. The code will be very similar to the one that we just demonstrated in the lecture. We will start by loading the image, then selecting the non-zero pixels and creating the feature matrix in the right shape. And these lines of code are already prepared for you. So your first task is to create the model. And for that, we first need to load the k-means clustering object, of course, from the Scikit-learn. So we write from Scikit-learn .cluster import k-means. And now we need to create the model, so it will be k-means. Here we need a parameter because we said we want 3 clusters, so we need to tell the k-means model. So n clusters equals 3. Okay, that's our model. Now we feed the model, model2.fit, and we will fit it to the feature matrix x2 that we created here. Next, we can predict the labels, model2.predict, again to the same feature matrix x2. And finally, we need to reshape these labels to the 2D image. So we will do this in 2 steps. First, we need to create a matrix of the same shape as our original image, and we will fill this matrix with zeros. So mp.zeros. And now in the argument here, we need to say what shape of this array we want. And we just want the same as the T2, so that's what we will say, T2.shape. Okay, and the final step is to input our predicted labels into the correct locations. So segmentation 2, and the locations are stored in this variable int2. That's it. And now we put the label vector y2 as here. So let's run it. And it works, but you can see one strange thing, that the cortex is the same color as the background, so that is the label 0. So this is because the k-means algorithm will predict labels 0, 1, and 2, but we already have background 0. So we would like to increase the labels by 1 so that they are different. So if I do that and run it again, then I get a nice segmented image where each class has different labels, label that is different from the background. Now I would like to demonstrate the solution to exercise 4. In this exercise, we will compare performance of a perceptron classifier to detect breast cancer using the original 30-dimensional features and reduced 2-dimensional features. This exercise is split into several cells. And in the first cell, we load the data set and extract the feature matrix and label vector. So we can just run this cell. Only thing to notice is that we will store the feature matrix in variable x and the label vector in variable y. The next step is to apply PCA to the feature matrix to reduce the dimension from 30 to 2, and check that the reduced matrix indeed has only 2 features. So here we already have imported PCA, but we need to create the model, so we'll do that, PCA. And we need to tell it how many principal components we want, and we said we wanted 2, so n components equals 2. Next step is to fit the model.fit, and we input the feature matrix X. So we don't input the label vector because PCA is, of course, unsupervised. And finally, we will apply this model. So we will transform the feature matrix. So model.transform X. Okay, so we transform feature matrix X to feature matrix X reduced. And here we have code already to print the second dimension of the reduced feature matrix. And of course, we expect that it's going to be 2. And there we go, we have 2 features. The next part of this exercise is to compare the performance of perceptron using the original and the reduced feature matrix. So if you remember, we need to scale the features when we are using perceptron. So we imported not only perceptron, but also standard scaler for scaling. So code for creating the perceptron is already there. Also code for the fitting. Just note that we have to apply the scaling, and we can do it quickly with one command like that. So the feature matrix X will be scaled when it's inputted to the classifier. We also need a label vector because, of course, the perceptron is supervised. And now we can calculate the score. So also, when we calculate the score, we have to apply the feature transformation, otherwise it wouldn't work. And we input the label vector. And here is the code to print out the accuracy. Now, your task is to do the same for the reduced features. So first we fit the model. So that's CLF classifier.fit. And again, we need to scale it. So scaler dot fit transform, but this time X reduced. We shouldn't forget the labels Y. And to calculate accuracy, CLF dot score. And again, don't forget to scale, scaler dot fit transform. A little bit of a typo. There we go. X reduced. And feature vector, label vector Y. Okay, so let's compare. And we see that original accuracy is 0.98 and the reduced accuracy is 0.92. So from this, we could conclude that original features are better, but we need to be careful here. One mistake that we made here is that we calculated accuracy using the same samples as we fitted. And sometimes this performance might not be the same when we use the samples that were not in the training set. And this is a problem, and we have to be careful. And we will talk about this problem in the final part of this lecture, part 4. So I invite you to listen to the part 4 now.